That was rhetorical. When I say you're ready, you say how high. Something like that. This time what we're going to do is I forgot the cats, I have cats. Determine if the functions are linearly independent or dependent on the whole real number line. So this time what we're going to do is we're mixing linear algebra and calculus. So I'm assuming if you're watching this, you're probably the engineers, and we already know what derivatives of a bunch of functions are, and then we need the Wronskian. So what the theorem says also is we want to be careful with this. We'll probably do another one, but for this one, what I'm going to do is if we calculate the Wronskian and then the Wronskian, which is a function of x, what we're going to build from these functions of x, if the Wronskian is actually non-zero for some number in the interval, and then because we're using r, we can pick any number in the real numbers, as long as we can find that the Wronskian is non-zero somewhere, then the functions are linearly independent. The theorem does not say if the Wronskian is zero everywhere, therefore the functions are dependent. There can be counterexamples. Check the textbook. They will always usually have at least one. I think the one they use classically in your book is this one. How do you take the derivative back? Too bad. But those two guys, when you take the Wronskian, when you take their derivatives and then compute the Wronskian, you end up getting zero. The constant function zero, so it's zero everywhere. But these functions are linearly independent, so you can't say their Wronskian is zero, therefore dependent. How we argue is if the Wronskian is not zero somewhere, then independent. If the Wronskian of these three functions, 1x and x squared, which is also a function of x, I'm taking three functions and building a function of x, happens to be the determinant of those functions, and then their derivatives in the second row, so 0, 1, 2x, and then I like polynomials, you always get upper triangle, and then the determinant is the product of the diagonals. Just a second. 0, 0, 2. So this is upper triangular, which means zeros are below the diagonal. If you have an upper or lower triangular matrix, the determinant is equal to the product of the diagonals, which is 2, which is not 0. We got that the Wronskian is, in fact, it is a function of x, and this one's weird for polynomials. What happens is it turns into a constant, so it's a constant function. So w, the Wronskian of x this time is just the constant function 2 for every x. So it's definitely not 0. So what that says is because the Wronskian is not 0 for at least one value, in fact all values, these functions are linearly independent. Matrix, all the information, oh, that was not a triangle, that was a quadrilateral of some kind. Let's try that again. Triangles have three sides.